In this next question, we have this boron chemistry. So this compound called diboron, B2H6, can be used as a rocket fuel. You react this BF3 with sodium borohydride. We just need to balance this equation very quickly. You have boron here and you have boron here. So you have two borons and another boron here. So it seems like the fluorine substitutes out or replace all the hydrogen. You get NaBF4 and all the... Yep, that is what happened there. And now the hydrogen has replaced the fluorine, but now you get B2H6. So let's think about how we're going to balance this. If I have one sodium and one sodium like this, doesn't look like it will balance because 3 fluorine, 4 fluorine. So the only way you can think about lowest common multiple, 3 fluorine and 4 fluorine. If you do the lowest common multiple of 3 and 4 is 12. So what we need is really 3 of that there. 3 times 4 is 12. 4 times 3 is 12, so 4 there. And what next? If we have 3 sodium, we must have 3 sodium there. And what next? If we have 4 times 3, which is 12 hydrogen, we must have 2 B2H6. And now what next? 4 boron plus 3 boron is 7 boron. 2 times 2 is 4. 4 plus 3 is 7 boron. This equation is now balanced. Okay. Part B, primary and secondary alcohols can be formed by reacting carbonyl compounds such as ketones or aldehydes because carboxylic acid cannot be reduced by sodium borohydride. So does not reduce carboxylic acid. To reduce carboxylic acid to primary alcohol, you need lithium aluminum hydride, which is a much stronger reducing agent. So this one can reduce ketone and aldehydes to their corresponding secondary alcohol and also primary alcohol respectively. You're supposed to complete this mechanism for this reaction with hydride ion. H minus has a lone pair on the hydrogen because it's got 2 electrons, it's not H plus. So this is your exact same mechanism as in AS chemistry, nucleophilic addition mechanism. So this is from the lone pair. I label the dipole. Rich in electron would attack the poor in electron. So the first thing that happens is rich attack the poor. Once the rich attack the poor, carbon cannot form 5 covalent bonds. So I have to break this bond here. And I gave the 2 electrons to the oxygen. Then I get O minus with a lone pair on the oxygen. That is called the oxy anion intermediate. Now I formed this bond between carbon and hydrogen. I've got an oxy anion intermediate where the negative charge is on the oxygen. I then add in H plus. H plus has no electron at all. So these 2 electrons on the oxygen, they just attack and pick up a H plus, and now you form an alcohol there for that 3 marks mechanism. Part C, boron is used to synthesize alcohol, so you can make alcohol from alkene. So this is not your usual A-level chemistry. What do we know? The BH2 group from BH3 bond to the least substituted. The least substituted means it has the most hydrogen. The most hydrogen, therefore the least carbon. Substituted with carbon, so the least carbon means the most hydrogen, because the more carbon you have, the lesser is the hydrogen. So if we look at this alkene, the least carbon is this one because it's got 1 hydrogen. This one hasn't got any hydrogen. It is the more substituted one. So that means the BH2 will go here and then the H will go there. That's what they're saying, right? The hydrogen will go here. You see, the hydrogen goes there onto the more substituted carbon because the BH2 add to the least substituted carbon, which is the one with more hydrogen and less carbon. So blah blah blah, and then you replace the BH2 and then it becomes OH as you do oxidation. This square bracket or here refers to oxidizing agent, so you must have some sort of redox that you can oxidize this group and then replace it such that the carbon gain oxygen, and this is called oxidation, gain of oxygen on the carbon. What type of reaction is step 1? You have just gone for alkene, you have just added something across the alkene. They are not looking for mechanism. Do not write mechanism in here because they're asking for the type of reaction as stated in the AS introductory organic chemistry terminology. This is going to be addition type of reaction there. Now this diol Y can be prepared by the same method. So now you want a diene. Diene means 2-time alkene, so 2-time carbon-carbon double bond, which could be used to prepare diol Y. So you could see the OH is here, and you must add onto carbon-carbon double bond. If my carbon-carbon double bond is there, so that means I've added that. And now if I draw another OH here, then I have another H here, so that means my another double bond is there. So I just remove that and I get the double bond, and I could get this, which is the other one. So I get the double bond there and the double bond there, diene, 2-time alkene, 1 2 3 4 5 6. So this is hex 1 2 3 4 hex 2 4 diene, as this is 1 2 3 4 5 6. In fact, you can call this trans, although they are not asking you on cis and trans. So you could draw the cis or the trans, it doesn't matter. You could draw the cis or the trans because they all will give you the diene when you prepare the diol by adding H and OH. This is addition of steam, which is H2O gas, and you need concentrated phosphoric acid catalyst, and you are not going to add steam if your temperature is below 100 degrees Celsius. So usually you need a heat which is around 300 400 degrees Celsius, somewhere along that line there. The structure, so you could draw skeletal or structural or whatnot, but essentially you must have 2-time alkene. So what I'm saying is you could also have this one, which is okay. You could also have this one, which is cis and cis. This one is going to be trans and cis. So these or the trans and the trans, they are okay. How about the cis and the trans? The cis and the trans is going to be the exact same molecule as this, because you could just rotate the molecule. You will see what I mean when you draw the cis and the trans, when you just rotate the molecule there. This next one is a long essay question for 3 marks. Describe the structure and bonding in benzene C6H6. This is as stated in the A2 syllabus. You must be able to do this. What I'm going to do really is I'm going to sketch out a picture, and they never said that you cannot show a simple picture. In fact, you can always show a simple picture to make your idea a bit clearer. So I've just shown that there are p orbitals on each carbon, and these p orbitals can overlap sideways, where the electrons hop around and then get delocalization. So this one is basically this thing here, where you have delocalized electrons. Okay, so what is the structure there? Simple covalent structure. That one is very obvious. It exists as individual single molecule, but they are not asking exactly on that. They are asking on what is happening. Each carbon has 3 bond pairs, because if I draw the cocoon structure, you can see it better. 1 2 3 like this. You have H, 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 and H. You count only the sigma bond. So 1 2 and 3 around each carbon. You have 3 sigma bonds, so 3 bond pairs, and you have 0 lone pair. And then this one will give you 3 bond pair repel equally. 3 bond pairs repel equally. This is your VSEPR. So therefore, trigonal planar geometry. So trigonal planar, 120 degree at each carbon. What else can you comment on this? This is carbon sp2 center. Each carbon has 1 unhybridized orbital, 1 p orbitals, 1 times 2 p orbital on carbon that remains unhybridized. That is the meaning of sp2, because you still have 1 more p orbital that you didn't hybridize, otherwise you will have sp3. And these 1 electrons in the 2p orbital that remain unhybridized, they can overlap sideways. Delocalizing the electrons, and therefore pi pi electron density. You get a pi electron which are rich in electrons above and below the plane. Pi electron density rich in electrons above and below the planar structure. So it is planar, it's completely flat. Alright, so this is just a sideway representation of things. What else can we say? It's not really, alternating single and double bond, as we know about the idea of delocalization. The electrons does get delocalized around, so they're not fixed like alternating double or single, but really it's like a partial, like 1.5, 1.5, 1.5, 1.5, 1.5, and 1.5 bonds that the electrons are always moving around like that. Okay, having said that, the rich in electron density above and below the plane is what makes benzene like to be the rich in electrons, and they will attack the electrophile. But this delocalization provides some sort of stabilization that after it does the initial addition and you lost a double bond there, you will always want to go back to being benzene again. Then you will kick out the H+. That is the special thing about electrophilic substitution mechanism. You want to go back to being benzene because of the resonance stabilization energy due to the delocalization of electron in the structure and bonding for C6H6 there. In this last bit of the question, this is 1 mark question. So they're saying that in borazine B3N3H6, so instead of C6H6, as you know, boron, carbon, hydrogen. So this is in group 13, 14, and 15. So number of valence electrons, this is 3, 4, and 5. When you have carbon and carbon, you have 4 plus 4, which is 8 electrons. When you have boron and nitrogen, you have 3 plus 5, group 13 and group 15. You also have 8 electrons. They actually look very, very similar. You can see that BN bond is actually shorter. Is it? No, BN bond is longer because single bond is weaker. Single bond is weaker. Weaker covalent bond is going to be longer covalent bond, and this is as stated in the AS syllabus under bonding. Whereas the BN bond is a double bond. The double bond is going to be stronger covalent bond. So stronger covalent bond is actually a shorter covalent bond. Okay, because of the stronger force of attraction between the localized shared pair of electrons and the 2 nuclei. So a shorter bond there. What else? This is what happened in reality. This is what happened in reality. You get somewhere in between. This is exactly the same idea of delocalization like in the C6H6 just now, where we say it's not exactly a single, it's not exactly a double. Instead, it's somewhere in between, somewhere like 1.5 kind of bond. So what we have from this information, you draw the structure, you have delocalization. That is the evidence of delocalization. So this thing here is the evidence of delocalization. So what you cannot do is you cannot draw single and double because of this information there. All of them are of the same length, and they are longer than a double, which means it's weaker than a double, but it's stronger than a single because it's shorter than a single bond. So what I do is I draw boron, nitrogen, boron, nitrogen, boron, nitrogen. Why do I do that? Because of this information alternate around the ring. If we know how to read the question, we know how to interpret it. And then of course what I do is I also have hydrogen, 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 hydrogen. You have lone pairs in the nitrogens and you have empty orbitals in the borons. So what actually happens is you must get a ring structure that represent the delocalization of electrons and not the single and double alternating bond, because even though they said this, they also mentioned that all of them are the same length because of the evidence of delocalization, just like what we had earlier with benzene chemistry. We draw this ring, we therefore draw this ring for borazine C6, not C6, B3N3H6 there. And that's the 1 mark question for the suggest kind of structure. So that's the end of that 10 mark question there.